The following content is provided by MIT OpenCourseware under a Creative Commons license. Additional information about our license and MIT OpenCourseware in general is available at ocw.mit.edu.
All right, so we're in the middle of acids and bases, and we're going to just finish up the handout from Monday starting first. And we're talking about relative strengths of acids. So if you have an equation such as this, there is acid-base chemistry going on in both directions. So in the forward direction, HNO3 is acting as the acid. It's giving up its hydrogen ion or proton to NH3. And when it gives it up, it's forming its conjugate, NH3 minus. And when NH3 accepts a hydrogen atom or proton, it's forming its conjugate acid, NH4+. So that's what's happening in the forward direction of this reaction. In the reverse direction of this reaction, NH4+ is acting as the acid. It's giving up a proton to NH3 minus. When it gives up the proton, it's forming NH3, the conjugate. And when this accepts the hydrogen ion or proton, it's forming its conjugate acid. So in this direction, this is the acid, and in the reverse direction, this is the acid. So you can predict something about where the equilibrium lies, whether it's to the right or the left, if you have a big K or a small k for this reaction, based on whether this is the stronger acid or this is the stronger acid. So if this is a stronger acid, the equilibrium will lie to the right. If this is a stronger acid, the equilibrium will lie to the left. And so we can take a look at this and work out which is the stronger acid and where the equilibrium lies. So here's the equilibrium constant for this reaction. Again, it would be products over reactants. And so to find this number, we can work through it by getting information about the Ka, or acid ionization constant, for this acid and for this acid. So we can consider the reaction separately. We can consider this acting as an acid and also this one. So let's start here and consider the forward direction of the reaction and consider how good an acid HNO3 is. So you all should be able to write reactions of acid in water or bases in water and figure out what the products are going to be of that. So if we have NH3 in water, then we're going to be forming hydronium ion and the conjugate base of this conjugate acid here. And then we can write a Ka, and it's a Ka because we're talking about an acid in water. So the Ka is going to be equal to the products over the reactants, and here water isn't included because it's the solvent. And its concentration really isn't changing through the course of this reaction. And we can look up an equilibrium constant for this acid, and that's 20. So is that a strong acid or a weak acid? How did we define strong acid last time? It was a Ka if it's greater than 1. So 20 is greater than 1, so this is a strong acid. Now we can do the same thing for the reverse direction. In the reverse direction, the acid is NH4+. So we can write NH4+ in water, and that would go to hydronium ions and the conjugate of this acid, which is NH3. We can write out a Ka expression for this. Again, it would be products over reactants. And here the Ka, which could be looked up, is 5.6 times 10 to the minus 10. So is that a strong or weak acid? That's a weak acid, so the Ka is quite a bit less than 1. So already we can predict that for this overall reaction, it will lie to the right. This is a much stronger acid than this one. But we can prove that that's true by using these two Ka values to get the overall equilibrium constant for this reaction here. So if we took those two individual reactions that we wrote out and subtract them, we can get our overall expression for the reaction. And if we subtract them, then we can come up with the K by dividing the Kas from each other. So remember, we talked about Ks. If you add together, you multiply. If you subtract reactions, you can divide. And so we can prove that this is true, that if we have the Ka up here and the Ka down here, it will cancel to form the equilibrium expression for the overall reaction. And we can substitute our Kas in 20 over 5.6 times 10 to the minus 10. And we get a K for the overall reaction of 3.6 times 10 to the 10, which is an enormous number. And so this would lie very, very far to the right. This is a much, much stronger acid than NH4+. So if you know something, if you have acid base on both sides of the equilibrium, you know about the strengths, you could predict where the equilibrium of an overall reaction is going to lie. All right. So this is still on the handout from Monday, and mentioned that there are 5 different types of acid-base problems that you're going to encounter in this unit. And there's problems of salt and water, which we're going to see today break down to a weak acid or a weak base in water problem. So it's really not a different type of problem at all. So there's weak acid in water, weak base, strong acid, strong base, and they're buffer problems. And when we do titrations, it'll seem like that's a different kind, but it also breaks down into these categories. So one trick that I've learned from teaching this a number of years is to get people starting to think about what type of problem it is whenever they see it, and figuring out then they know how to address that problem. So always be thinking about what type of problem is this, and so how do I go about solving it. So we're going to look at the first, number 1 here, a weak acid in water problem. And the weak acid that I picked to look at is vitamin C. So in this particular problem, we are going to ask what the pH would be if I take this vitamin C tablet, and it's a 50 milligram tablet, and put it into 100 milliliters of water. And usually when you try to swallow vitamin tablets, you try not to dissolve them. But if we did, then we could look at the pH. I've discovered, though, I actually tried to do the calculations and do the actual experiment one year and discovered that these vitamin C tablets are coated really well. You cannot get them to dissolve very easily. And so that's because you don't want the bad taste in your mouth. So nature's bounty, if you don't want this tablet to dissolve in your mouth before you swallow it, I guarantee it won't. You have to go to extreme lengths to get this to dissolve in your mouth. So we can't actually measure the pH of this because it's not going to dissolve. The coating is pretty good. But we can do the calculations if the coating was less good, what the pH of that would be. All right. So the first thing we need to know is molarity. And so you can do this calculation. You know the number of milligrams, convert to grams, look up the molecular weight, calculate how many moles that is, and then that number of moles in your 0.1 liters or 100 milligrams, and you can get the molarity of a vitamin C tablet in 100 milliliters of water. Then you would need to write the equation for a weak acid in water problem. And so here's our weak acid in water. It's forming hydronium ions and a conjugate base. So then you can set this up and figure out what happens as initially the change and then what the concentration would be at equilibrium. So in the beginning, you just have this molarity, the 0.0284 molar solution, and you don't have any of these initially. The change would be minus x, and then plus x plus x. So at equilibrium, we're 0.0284 minus x, and again, plus x. So now to solve for x, which is what we want to solve, we want to find out pH. And pH is the minus log of the hydronium ion concentration. So we need to find x to be able to find pH. And to get x, we can do that if we know the Ka for the solution, write out the expression, hydronium ion conjugate base over acid. We're leaving out the water again. So that would be equal to x squared, 0.0284 minus x. So now we can try an assumption, and this will be useful to you on exams. So first you can try to say, what if x was really small? What if x was much, much smaller than this 0.0284? Then this term just collapses into the number. So you can make that assumption and try it and see if it works. And I'll tell you what the rule will be to check that out. So if we try the assumption, then we have just x squared over this number. That's easier to solve. And we can solve for x. And here x is 0.00151. And I'm carrying an extra significant figure. And then we can go and check, is this true that that is, in fact, much smaller than this? And the rule that we'll use is 5%. So you can calculate whether the number is 5%. Take x over your initial number times 100%. In this case, it was 5.3%, which is more than 5. And so you should use the quadratic equation to solve for x. So most of you normally use calculators, which there's no problem in doing quadratic. But of course, the calculators we use on the exams are not so amenable to doing this. So I suggest on an exam, you always try the assumption that you can make it a simpler problem to save yourself time. So the rule is 5%. It has to be less than 5%. So I'll just mention that the book talks about this expression and refers to percent ionized or percent deprotonated. So this equation, which is really x over the number minus the initial molarity minus x, is how much you've gone to that side of the equation, how much you've deprotonated, what the percent ionization is. So you'll see those terms in the problem set and in the book. So if you use the quadratic equation, then you get 0.00147, and we're still carrying an extra significant figure. That's really two significant figures. The Ka just had two significant figures that was given. And so if we now solve, so this is x, when x was the hydronium ion concentration. So pH is minus log of the hydronium ion concentration, which would be 2.83. And since this was really two significant figures, now you have two significant figures after the decimal point. So that would be the correct significant figure number for this. So remember this 5% rule to make your life easier, and also in all of these problems, you want to pay attention to the significant figures. Again, the rules for logs and significant figures are a little complicated and require some thought. All right, so that's weak acid in water type problem. And the weak base is going to be very, very similar to that. And so today we're going to be going on and talking about weak bases. We're going to talk about salt solutions, and I'll try to prove to you that salt solution problems just break down to weak acid problems and weak base problems. Yeah?
When you have the evacuation equation, you have x squared over a certain number minus x. Those two x are different x's?
No, that's the same x.
If you take one x as big, infinitesimally small, doesn't the upper term collapse to zero?
It's just smaller than, it's just a question of it's smaller than the number. So back here, it's not that it's incredibly small number, it's just within the significant figures smaller than this number so that if you subtracted it from that number, it wouldn't really make any difference.
Right, but if you go like about 2 slides back or something like that.
This one?
Yeah, because that one says x squared over 0.028 minus x, and then at the bottom it says k blah blah equals x squared.
Yeah. So this is the assumption that x, the number x, is going to be enough smaller than 0.028 that if you subtracted x from that number, you'd still get that number.
Right, but the question is that x is there as being x on the top.
Yeah. So here you're getting plus x. You're forming this amount of hydronium ion, this amount of the conjugate, and that's the same amount that's forming here that what you're taking away from your initial over here. So it is the same x. So you're not really saying that this is infinitesimally small number. You're just saying that it's smaller than this to the degree that it's not playing a big, it's not changing this very much, so you don't have to actually do that subtraction. And so the rule we use for that is 5%.
Thank you.
Okay. So again, there are these types of problems, and now we're going to look at a weak base problem. Okay, so let's look at a weak base problem. I need better chalk than that. All right, so weak base in water. So if we have NH3 plus water, it will go to the conjugate of NH3, which is NH4 plus, and hydroxide ion. So if you're talking about a weak base in water problem, you're going to expect to see hydronium ion on the other side. And this is just a check that you want to make sure you're asking yourself as you're doing these problems. If you write the equation wrong, you're going to be in a lot of trouble. Weak base should yield a basic solution, so you should be getting hydroxide ions out. All right, so if we look at this problem, we have an initial concentration of 0.15 molar, and we don't have any of this, and we don't have any of that. The change is going to be minus x, plus x, and plus x. Then at equilibrium, we'll have 0.05 minus x, and we'll have x and x. So now it's a weak base in water, so we're going to talk about a Kb. And so Kb is the base ionization constant. So Kb is also going to be equal to the products, because it is an equilibrium constant, products over reactants, and we're not including water because it's the solvent. So this will be equal to x squared over 0.15 minus x. And we can try this assumption again, that might be equal to x squared over 0.15. So the Kb is given, and for a lot of the problems, you'll be able to look this up in your book, of 1.8 times 10 to the minus 5. So again, it's a weak base. It's less than 1. It has a Kb that's less than 1. And so if we solve for x here, we get x as 0.00164. And now we can check our assumption that that is okay using the 5% rule. So 164 over 0.15 times 100 gives you 1.1%. So you're checking the assumption, and the assumption is okay. It's less than 5, so we can use that number. All right, so now we want to find out the pH of this mixture at equilibrium, and we have X. X is equal to the hydroxide ion concentration. So we can calculate first POH minus log of the hydroxide ion concentration. And so we have minus log of 0.00164, and we get 2.79. So this only had 2 real significant figures. We're carrying an extra one. We only had 0.15. We only had 2 significant figures here. So this is going to get 2 after the decimal point. So our number would, since we have 2 here, we get 2 sig figs after decimal. So now we have POH. How do we get pH? Yeah, we can subtract from 14. So the pH is going to equal 14.00 minus 2.79, and it'll be 11.21 will be the pH. And I just want to remind people, sometimes when you're in a hurry on a test and you get to this point and have this number of 2.79 and you say, oh, I'm done. But that's the POH. And if you think about it for a minute, a weak base in water, a base in water should give rise to a basic pH, i.e. a pH greater than 7. So below 7 is acidic, above 7 is basic. So you have to remember to convert to pH. The pH should be a basic number. So just keep it in mind as you're doing these problems. Think about what the problem was. Oh, it's a weak base in water. Does my answer make sense? To kind of double check that you've gone the full direction. Okay, so that's weak base. Now we're going to talk about salts in solution for a minute. And salts in solution are going to break down into weak acid and weak base problems. So if you have a salt can be formed by mixing an acid and a base, as shown up here. But the pH of salt water is not always going to be neutral. So if the salt contains, for example, the conjugate acid of a weak base, then it contains a conjugate acid, so it'll produce an acidic solution. Also, salts that contain some small highly charged metals, like iron 3+, will also affect the pH. This is something that you should remember. Group 1 and Group 2 metals, or metal cations with charges of +1, and we have lithium, calcium +2, silver +1. These are all going to be neutral, but other things like iron 3+ will not be. Or if you have a salt that contains a conjugate base of a weak acid, it's a conjugate base, so it can produce a basic solution. So if you remember, on Monday, we measured the pH of MIT tap water and found that it was not neutral. It was pH 6 rather than 7. So that would suggest that there was some salt in that tap water that was giving rise to a non-neutral pH. So in terms, this is also a review from last time, there's this relationship between the conjugate acids and bases. So this isn't in your handout, but just to remind you what we were talking about. If you have a strong acid, its conjugate is ineffective as a base. If you have an acid that's moderately weak to weak, then it will have a conjugate base that's also moderately weak to very weak. And if you have a really strong base, then its conjugate will be ineffective as an acid. So there's this relationship. All right, so let's take a look at some examples of salts. So if we have NH4Cl. If you're asked whether putting some amount of this in water will lead to an acidic solution or a basic solution or a neutral solution, this is how you would approach the problem. First, you're going to break this compound through the middle and consider two sides. You'll say this salt would be composed of NH4 plus and Cl minus. Then you're going to ask whether this is a conjugate acid of a weak base. So, is this a conjugate acid of a weak base? If it is a conjugate acid of a weak base, then that will affect the pH of the solution. So what's the conjugate of NH4 plus? So the conjugate of this is ammonia. So the weak base, if you take the weak base, so the conjugate, the weak base, is NH3. And if you added a proton to this, you get the conjugate acid, NH4 plus. So this is a weak base. So the answer to that question was yes. You could look it up in the table. Here's ammonia. It has a Kb that's fairly small, so it is a weak base. And we also had it on this chart. You had NH3 over here, and so you could see that it is in fact a weak base. And we can look up the Kb for that. And so the Kb is 1.8 times 10 to the minus 5, so that's a weak base. So because the conjugate is a weak base, that means that the conjugate acid is also a weak acid, and so this should be acidic in solution. So that should be acidic in solution. And let's just write that out over here. So if we have NH4 plus, and that's got to be a weak acid because its conjugate is a weak base, and we put the weak acid in water, we should get the conjugate base back plus hydronium ion. And the presence of the hydronium ion is going to make that acidic. And so this is a weak base over here. Its conjugate is a weak base. And we can look up a Ka number for it, 5.6 times 10 to the minus 10. So that is, in fact, a weak acid. And so here it is on this table. We can look it up, and it is a weak, it's less than 1. It's definitely a weak acid. So this part on this side of the compound, we have something that's going to produce an acidic solution. So now we have to ask, well, what about this side over here? And so we would ask, is this a conjugate base of a weak acid? Is Cl minus a conjugate base of a weak acid? What would be the acid, the conjugate acid of Cl minus? HCl. So the conjugate is HCl. Is that weak? No. So this is a strong acid. And that's one that you'll encounter a bunch, so you'll definitely have that memorized by the time you get through the problems. So it has a Ka over here of 10 to the 7th. So if you put that in water, if you had HCl in water, it's a really strong acid, Ka 10 to the 7th. And so it would go pretty much all the way to completion. So that means that this would be ineffective as a base if you have a strong acid. Again, there's these relationships that we talked about if something is a really strong acid up here, then its conjugate is completely ineffective as a base. So this then is going to be neutral. So because this is not going to change the pH anymore, it's ineffective as a base, it's not going to make the solution basic at all, whereas on the other side, NH4 plus is a conjugate acid of a weak base, so it will produce an acidic solution. So the answer is that this salt in water will be acidic. So if you were given an amount of this compound, if you said 0.15 molar, for example, what is the pH? You could work that out by just doing a weak acid type problem and solving for X here and calculating pH. So this particular salt in water problem is just a weak acid in water problem. Okay, let's look at another example. Okay, again, we're going to take this compound and break it up, and we'll form Na plus and CH3COO minus. So then we ask, is this a conjugate acid of a weak base? And what's the answer? Where do you think it probably came from? Yeah, it probably came from NaOH. So this one, the answer here is no. And we talked about rules that all group 1 and group 2 are neutral. Group 1 ions are neutral. Group 1 and group 2 are neutral. So this in solution will be neutral. All right, so let's look at the other side and ask, so is this the conjugate base of a weak acid? And what would be the acid here? Yeah, acetic acid. So we have CH3COOH. And we can look to see if that is a weak acid. And we can look it up here. And so we have, so you get the right line, 1.76 times 10 to the minus 5. So is that a weak acid? Is that a weak acid? Yes. So if it's a conjugate base of a weak acid, then in solution, it's going to be basic. And we can work that out if we wrote it out. We have CH3COO minus in water is going to yield hydroxide ions and the conjugate acid over here. And the presence of this will make, of the hydroxide ion, will make the solution basic. So this is a weak base on this side. And so if you were asked, given an amount, you could solve the problem using the Kb of the weak base, solving for OH minus, finding POH, and then pH. So overall, this salt in solution will give rise to a basic solution. So you'd have should have a pH greater than 7. So this salt in water would give rise to a basic solution. And this salt and water problem breaks down into a weak base in water problem. So let's just do the generic. The generic type of problem. So in the general case, if we have made up compound XZ, made-up compound XZ will break down into X plus and Z minus. And you're going to ask, is this a conjugate acid of weak base? And or you're asking, basically, is this going to be acidic? So if the answer is yes, if you have a conjugate of a weak base, which is a weak acid, you will have an acidic solution. If the answer is no, you will have a neutral, at least in terms of the X. On the other side, for the Z minus, you're asking the question, is this a conjugate base of a weak acid? If it is a conjugate base of a weak acid, then it's going to be basic. It will be a weak base. And so the answer is yes, you're going to get a basic solution. If the answer is no, here it will be neutral. And in these problems, in the short answer type format here, you're not going to be given a case where one side will be acidic and the other side will be basic, because then you can't give a short answer to that problem. You'd have to figure out which one was more acidic and which one was more basic. So in these types of problems, one side will always be neutral, or they could both be neutral. You will see examples where both of them are neutral. But you're looking at each side and asking a question about it. So that's how you go about doing these salt and water problems. All right, so this leads us right into buffers. So buffers, this is another type of problem that we will have. And again, you're talking about weak acids and weak bases here. So a buffer is any solution that maintains pretty much a constant pH despite the addition of small amount of acids and bases. So buffering is all about constant pH. An acidic buffer is just a buffer that's going to pH or stay sort of a constant pH in the acidic range, so the acidic side of neutral, and it would consist of a weak acid and its conjugate base supplied as a salt. A basic buffer will have a weak base and its conjugate acid supplied as a salt, and it's going to buffer on the basic side of neutral. So that makes a lot of sense. All right, so let's look at a buffer example. So in all buffers, you're going to have an acid mixed with its conjugate in the form of a salt to get a dynamic equilibrium. And so if we have this, we have the acid and its conjugate added here. And we ask, what happens if you add a strong acid to this solution? And because, again, what we want to have a buffer do is maintain a constant pH. So you need to have about the same amount of this guy as this guy for that to be true. So if you added strong acid and you had some of this and some of this, the acid is going to react with the conjugate base and drive it in this direction, using up the amount of strong acid that was added. So the added acid, hydronium ions, are effectively removed, and the pH stays pretty much constant. Now what happens if you add a strong base? Well, a strong base is going to react with the weak acid over here, and it will also be consumed. And so you are taking the OH here is removing a proton. It's reacting with the weak acid, and it'll form more conjugate base, and it'll also form water. So again, it's effectively removed, and the pH stays pretty much constant. So a buffer should be a source and a sink for added problems to the reaction. It's going to use up either the acid or the base that's added and keep the pH pretty much constant. So again, what's happening is that the weak acid that you use, and you can have anyone there, is going to transfer protons to this, and that will cause the reaction to happen and use up the hydroxide ion. A conjugate base that's added to as a form of a salt, it would then be able to accept protons from any acid that's used. So you need both the weak acid and the conjugate base added in the form of salt. One will react if you add extra acid. One will react if you add excess base. So why wouldn't a strong acid and the conjugate base of that strong acid, why wouldn't that make a good buffer? Yeah? Yeah, right, because the conjugate base would be ineffective as a base. And so the strong acid would go to completion, will drive to the right. This is ineffective as a base, so you're not going to push it back the other way. So you're only going to have a good buffering system with a weak something and its conjugate that's also a weak something. So a weak acid and its conjugate weak base, a weak base and its conjugate weak acid. That will buffer because it'll go both directions. So both conjugates have to work as an acid or a base. If you have a strong acid, then its conjugate is ineffective as a base, it won't work. If you have a strong base, then its conjugate is ineffective as an acid, and it won't work. All right, so base buffering example. Same stuff applies here. So if you add a strong acid, it will react with the base. The base will accept the protons and make more of the NH4. And it will use up the strong acid. When a strong base is added, it'll react with the conjugate acid and go the other direction. And so you'll form more of the conjugate base in water. Again, the pH is staying the same. You're using up the strong base that's added. So in a buffer action, you have a weak base accepting protons supplied by the strong acid, and you have the conjugate acid of the weak base transferring protons to the hydroxide, the strong base that's added, using that up as well. So again, it's about going both directions of the reaction. That makes something a good buffer. So a buffer mixture of a weak conjugate acids and base stabilize the pH of a solution by providing a source or sink for the protons. So either they're providing a source to neutralize the OH that's minus, or a sink for the protons that are added in the form of acid, so the pH stays pretty much the same. So you need something that can do this dynamic equilibrium to be a good buffer. All right, so let me just give you, last couple minutes, an example of why buffering is important from a human health perspective. All right, so your blood is buffered around a neutral range. And the buffering agents are shown here. Carbonic acid and bicarbonate are effective as buffering agents. So they can provide the source or sink for added stress to the system, for added acid or added base. So your blood is buffered. And this is really important. If your blood pH changes, enzymes are designed to work at particular pHs. Molecules are not necessarily stable at certain pHs. So our body would not work well if it was not appropriately buffered. So let me give you an example of a genetic defect that it overwhelms the buffering capacity of the blood and leads to a condition. So this is an enzyme that you have in your body. It's in your mitochondria, and it requires vitamin B12. And this is what the enzyme is involved in. It's involved in breaking down fatty acids to form energy. So most people like this enzyme. They're very happy with this enzyme. Most people want their fat converted to energy. And so this enzyme helps out with that going on. All right, so what happens if you have a genetic defect or if you don't have enough vitamin B12? But in this case, we're talking about a genetic defect. This step is blocked. So your body's making a lot of methylmalonyl-CoA, and it doesn't know what to do with it. It's a huge amount. And so it actually gets excreted from the body in the form of an acid. And so this leads to a condition known as methylmalonic aciduria. So there's so much of this made, you're excreting like a gram of this acid every day. The blood is overwhelmed. It can't handle that much acid. Its buffering capacity isn't that good. All right, so what causes this problem? So I'll tell you that this now is the amino acid sequence of the enzyme. So enzymes are made up of multiple amino acids strung together in a polypeptide chain. And down here's the number 721. So this is a lot of amino acids. And at the time, there were these babies born with this condition, and the doctors didn't know what to do to treat them, and a lot of the babies died. So a number of them got together, and they tried to sequence the gene. Now, of course, there's the Human Genome Project, so we know a lot of the sequences of genes. But the doctors sequenced this gene, and they sat down with the parents and said, okay, there's a mistake right here, where that red arrow is. It should be a glycine residue, but it's something else. All right, so imagine you're a parent, you have a kid, and the doctor tells you, there's a mistake right here. Okay, well, that's fantastic. What are you going to do about it? Well, at the time, the doctors had no idea what to do about it because they didn't really know what was going on here. So this answer partly came through structure determination. And they found that vitamin B12 changes shape when it binds to a protein. So here's vitamin B12. It has this group up attached to the cobalt when it's free. When it's bound to the protein, it looks like this. This long group is extended into the core of the protein. So the protein needs a big hole to put this group. And so this is a model of what the protein looked like. And here's a model of vitamin B12. So we discovered that it fits like this. It's fantastic. There's a huge hole in the protein into which you can put the vitamin. So how did nature create a hole? How did it make this space for the vitamin to fit? And then with the vitamin bound, it's active. So what it did was it put the smallest amino acids it could find over here. Now, what happens in this mutant protein is that one of those small amino acids was converted to something larger in the dark blue. So this was the protein that these babies had. And the doctors kept giving them more B12, more B12, more B12, and it didn't do any good at all because no matter how much you gave, it couldn't bind. It was blocked. The binding was blocked. So this suggested to doctors that instead of giving them the full vitamin B12, basically take a pair of scissors and chop off part of it and create something that looked more like this, and then try to see if that would then bind to the mutated protein. So that's the kind of thing that they were looking at, trying to alleviate this particular condition, because the buffering of the blood is pretty good. If you could restore some activity, get rid of some of the acid, you might be able to have a more normal pH. Okay, have a good weekend.